Hi everyone. Today an example of what I call a reverse icebox question. Here we go. A certain amount of A was injected into a 1.0 liter container. At equilibrium, it was found that the concentration of chemical C was 0.36 moles per liter. According to the reaction below, if Kc, the equilibrium constant, was 2.205, determine the initial concentration of chemical A. So here we go. The first thing is, this is an icebox question. We have a sentence describing an initial situation. Here's our phrase, was injected. We have a second sentence that starts with at equilibrium. This is the telltale sign that we have an icebox question. We set it up like this initially, some implied change occurred, and we arrived at equilibrium. So here we go. We're just going to start to fill in our icebox as we would normally. I, C, E. We're just going to take it one step at a time. A certain amount of A was injected. We don't know what amount that is, but it had to be something. We don't know. It was an undetermined amount of chemical A, which we're going to call here X. If you want to call that Y or Z, put a question mark there. That's all good. I recommend an X. It's our common unknown variable. This first sentence does not mention chemical B or C. So they must have been 0 initially. We look at the following sentence. At equilibrium, it was found that the concentration of chemical C was 0.36 moles per liter. We have the molar concentration. It's at equilibrium. It's chemical C. Goes right here in the icebox. E for chemical C, 0.36 moles per liter. We can tell that if it started at 0, the chemical must have experienced positive change, or it went from 0 up to 0.36. That's a positive change of 0.36 moles per liter. Because chemical B is on the same side of the reaction as C, it must have experienced the same type of positive change, or it was at 0 initially, it couldn't go down. It can't go down from 0. That's a positive change. But B is in a 1 to 2 ratio with chemical C. The change is going to be half as much. Half of 0.36 is 0.18 moles per liter. And 0 plus 0.18 is 0.18 moles per liter. We know for chemical A that it must have experienced negative change. Negative change. A is in a 2 to 1 ratio with B and a 2 to 2 ratio with C. So we can start by thinking about chemical B, a 2 to 1 ratio, 2 times 0.18. Or we can use the same number as chemical C because A and C are in a 2 to 2 ratio, a 1 to 1 ratio. This is going to be negative 0.36 moles per liter. To fill in the E part of the line here, we can't say for sure what the number actually is, but we can do this operation. X minus 0.36, that equals X minus 0.36 moles per liter. We have the equilibrium constant given to us, 2.205. So now what we're going to do is set up the equilibrium law and solve it for the unknown concentration of chemical A. Here, equilibrium law is equal to the concentration of chemical B multiplied by the concentration of chemical C squared, because it's balanced with a 2, over the concentration of chemical A, also squared. What we want to do now is manipulate the equilibrium law to solve for chemical A. This turns out to be the concentration of chemical A is going to be equal to the concentration of chemical B multiplied by the concentration of chemical C squared divided by the equilibrium constant, and that's all going to get square rooted. Again, we can take our time with this manipulation, or if you feel comfortable doing it all in your head, we need to arrive, though, at a manipulated version of the equilibrium law where we're solving for the equilibrium concentration of chemical A. Once we have that, we can move forward with our substitution. Let's put some numbers in. This means that it's the square root of the equilibrium concentration of chemical B, or 0.18, 0.18 moles per liter. Concentration of chemical C, 0.36 moles per liter. That's going to get squared over Kc, the equilibrium constant, which we can find in the question, 2.205. 2.205. Remember, that whole thing is going to get square rooted. Let's do the operation. 0.18 times 0.36 squared divided by 2.205. Take the square root of that. We end up at 0.10285714.3. That's the equilibrium concentration. That's the value that would go right there. Okay? And so, but we're not worried. We don't want the equilibrium concentration. We want to determine the initial concentration of chemical A. This is going to mean that our answer, 0.10285, our answer down here, moles per liter, equals X minus 0.36 moles per liter. And we're going to solve for X. So here, X is going to equal our answer, 0.10285. That number is still here on our calculator screen. And now we're going to add the 0.36 to it. Add 0.36 moles per liter. That number is already on my screen. So then when I add 0.36 to it, I end up at 0.462857143, which is my raw answer. I need to go back and consider the significant digits in the question. 0.36, that just had two significant digits, so we want our answer to have two significant digits, which turns out to be here, 0.46. This was the concentration that we were solving for in moles per liter. So this style of question, which I call a reverse icebox, is presented to us in the same way as a typical icebox question. Multiple sentences, a sentence that describes an initial situation, and a second sentence that starts with at equilibrium. So we set up the icebox as best as we can using some unknown variable because we had an unspecified amount. Then we do our best to solve the icebox, again, moving from column to column on the change line using mole ratios, set up the equilibrium law, manipulate it appropriately, substitute, solve. Then we have the additional extra step where we had to do the algebra here to work backwards to solve for the unknown initial concentration X. And I hope that helps.